Okay, good afternoon, and welcome to Sunoikisis Digital Cultural Heritage Fall 2017 semester. This is the 6th session, which will be on data structuring, querying, and visualization. This week, my colleagues Tom Elliott and Rada Varga and myself will be leading the session. Tom is first going to talk about some concepts of structured data. I will talk a little bit about how one queries and transforms data, and then Rada will talk about data visualization techniques. And all of this should be seen as a precursor, a lead-in to next week's session on transformation of various different data formats using Python, which will be presented by Simona and Matteo. We'll very much look forward to that next week. But so to start us off this week, I'll hand over first to Tom, who will take us away.
Right, greetings. Good morning from my end of the connection, and we'll just go straight to the slides if you'll be patient for a moment. Right, can someone confirm that you are seeing the slides for session 6?
Yep. So good.
Right. Okay. So as Gabby suggested, I'm going to be talking about data formats and classes of structured data. This is very much intended as an introduction to some basic concepts in data structuring. It will dip into various aspects of that, and it looks like I've actually deprived myself of my speaker notes. Which is going to be a little bit of a challenge this morning because I've lost my second screen. Hold on just a second. Let me see if I can work this out. I may have to present in a slightly different manner because I hadn't counted on being where I am. The problem with that's going to be that you all will have to look at another tab. Just a moment. And I'm going to have to adjust my sharing. Apologies.
No worries, take your time.
Okay, now you're just seeing a new tab, but if you'll be patient for a moment, we will get the presentation going there. And we'll make it as big as we can, so with as little extraneous junk as we can. I apologize that this means there's extra stuff in your view. I hope it's relatively readable.
Looks okay from here, yeah.
Okay, thanks. All right, so now let me get my notes. There we go. Right, so what I want to do is step through some basic structures in the kind of data. You'll see things that we've already addressed or presented in previous sessions, but we'll try to frame them a little bit more conceptually. We're going to start with this notion of a table because a lot of the data we've been talking about is either structured with a table in mind or it's been represented in tabular form. What is a table, after all? Well, in the first instance, it's a visible graphical layout for presenting regular data in quantity. So it's a mechanism that was invented in ancient times for presenting data to a human and for facilitating various kinds of tasks. You can find lookup tables of numerical calculations in Babylonian texts, so on and so forth. So it's meant to facilitate various kinds of reference and lookup. And initially designed with humans in mind. And of course, as any such thing, there's lots of variance. The main thing we want to focus on for our presentation today is that a table arranges data in a rectangular grid. You're looking at one here. We can talk about portions of that grid, and by reference, the data that appears in those portions. So here in green, we have highlighted one or more rows in the table, and row is the basic technical term we use for this horizontal slice through the tabular data. If we move on to our next slide, we can also talk about columns. In the same way that we talk about rows, and then we can highlight a individual cell. So rows, columns, and cells are the basic functional attributes of a table, the things we can refer to. And you can think of a cell as being a single selection out of everything in the table, or you can think about it as the unique intersection of a single row with a single column. One more characteristic of tables when we talk about selecting data out of them are groups of cells. These are sometimes called ranges, and normally when we say a range or a group of cells, we're talking about some kind of a contiguous rectangular selection. It might be some number of whole rows or some number of whole columns or a subset thereof. That would be a range of in a table. It's common when we want to make reference to things in a table or in a portion of a table, we want to have some coordinate system for referring to ranges, cells, rows, columns, and so forth. And the general convention is to either number or letter both the rows and the columns. The numbering is a convenient way to sometimes capture the order in which data is presented or the order in which data has been created, but it can also just be a way of assigning unique identifying numbers to a row or a column. It's very common for columns to have descriptive titles or headings, and this is something we get from print as well. And so you'll find table columns, both in data and in presentation, often have descriptive titles or headings. In computing, tables can be used not only to present data visually for human consumption, they're also an underlying logical construct that's suitable to the storage and management of some kinds of data. Word processors, you'll be familiar with the fact that they provide for the layout of information in tabular form. And there's special elements in the hypertext markup language that allow for similar presentation in web pages. And of course, if you've used a piece of spreadsheet software at all, LibreOffice or Numbers on the Macintosh or Microsoft Excel or something like that, you'll be familiar that those programs use the table as the primary visual interface metaphor for working with data. But we can also, as I mentioned, focus on tables as mechanisms for the programmatic storage and access of data, and as human-friendly metaphors for facilitating human interaction with more arcane data storage structures. So tables are the core organizational data structure or data structure metaphor in the most commonly used database systems today. So FileMaker, MySQL, Oracle, Postgres all make heavy use of the table. We can use such software, such database software, to capture information about the real world. For example, we might enumerate and describe the coins found when excavating an archaeological site, or the incidences of a particular technical term in a group of ancient texts, or maybe historical persons who are thought to have been associated with a particular ancient state or a government office or a historical event. We usually view tabular data as humans, formatted in the manner I've already described. But when you're serializing or producing that data computationally for storage or transfer, formatting is not the primary, formatting for visual purposes is not the primary concern. Instead, we want to format them in a way that another piece of software can successfully extract the data and work with it in exactly the same way it was created. So what we do is we take special characters called delimiters, or we use some other computational mechanism. But either way, we divide each cell's data from another. And in the case of the well-known comma-separated values format, which is abbreviated as CSV, and which we've seen already and we'll see again, commas are used as delimiters between cell values in a given row of the table. And then rows are delimited with new line or carriage return characters. And there's some variation system to system in what kind of character appears at the end of the line. But the basic idea is the same. It's a line. It's a row in the table. And you don't see it in this particular example, but you can even put commas inside an individual cell, provided that you enclose it in some other set of delimiters, and usually these are quotation marks. So sometimes we enter data into and read data from a database as humans in a table, but there are some other mechanisms that are commonly used, and there are different terms that go along with them, even though behind the scenes table are being used. So we'll talk about tables, rows, and columns and cells, as we've been doing, but we're also going to talk about records and fields. These are two terms that derive from some other pre-computing data management practices, namely note cards and paper forms. So the term record is often used to describe the full set of information that's entered or displayed in a single form. So in the simplest cases, the term record corresponds to a single row in the underlying table of information, but we're not required for that to be the case. There can be a more complex relationship. But this first example, that's what we're looking at. There's an entry form, and it corresponds directly to a single row in the table. And so each time you move your focus from one row to another, you are looking at filling that form with different information. We use the term field to identify or describe a single text box or other single data entry affordance on the form. And usually that field then corresponds to a single underlying cell in the table, as illustrated here. You should be aware, though, that the word field is also sometimes used more generally to refer to a particular column in the table. So we would talk about the mint column in this particular table, and we might say, well, in the mint field, you put things like. So that kind of an extrapolation or extension or abstraction can creep in, and you want to be aware that the term is a little bit slippery in that way. Here's my slide to demonstrate how much we love coins. But more importantly, this is a slide that's meant to help introduce us to another way of thinking about this process and the structuring of data. So a table and a form in a database, these are tools for humans to use to capture information about an object of interest, so a coin. And these objects can be physical, conceptual, or abstract, depending on the research task at hand. Information scientists also use the word entity to denote some object of interest that has a particular nature or classification. And so here we have a human being thinking of conceptualizing this thing, a coin, this entity. The descriptive terms we use to describe an entity in information science we normally call these attributes. A database table holds information about entities. The attributes describing each entity are arranged in rows, one row per entity. And then the columns proceed attribute by attribute, and their order is either arbitrary or of interest for some computational purpose. But anyway, here are some examples in these strangely polygon-shaped drawings of attributes associated with this particular entity, which we would call a coin. Some other internal data structures and external serialization formats can organize or present the data differently from the table, though. So here is an example of JavaScript object notation, which uses an object-oriented approach to presenting information, and this corresponds to some computing structures that are internal to software frameworks. And what you see here is the entity described in a serial fashion with each attribute introduced one after the other, rather than it being a tabular presentation of data. So if you had additional coins, you'd have more examples of these series of the attributes. So you're putting the object first rather than the structure of the attributes first. And we might find information presented in JSON even when it's coming from a system that stores the data internally in tables. So we need to get flexible with thinking about the difference between a tabular data storage structure or some other data storage structure and the format that the data is produced or serialized in for some other purpose. JSON's designed specifically to support online web interaction at the level of individual conceptual objects or entities. Hence, this kind of reorienting of the focus. Now, a table works well for basic description of a series of entities, but trouble can arise as the number and complexity of the attributes increases, and we run into several kinds of problems, especially around repetition. We want to be able to make use of regular terms. We want to be able to make use of controlled vocabularies. We don't want to have to type them over and over. We can also run into situations where we have multi-valued attributes. Let's say any number of place names for a given place. Do you put a separate column in the table for each and every possible place name? How many possible place names might a single place have? We can also have situations where we're trying to model densely interrelated but distinct classes of information, for example, people, places, and governmental offices, and we want to make sure that we're always referring to each of these by the appropriate name, that we're not confusing them with each other even if they have the same name, and that we're not repeating information that we don't need to repeat. Here, for example, is some coin data where you can see a lot of repeating values, and it would be nice not to have to type all of them and keep track of all of them. We can use groups of tables that are related to each other to handle these kinds of distinctions. So here's an example where we have two tables. One is providing the basic information about coins, and the related table is providing information about the mint locations, and particulars providing a home for their coordinates, so that we don't have to keep repeating the coordinates in every single row in the coins table. This process of breaking things out into these separate tables that are related to each other in this way is called normalization. And the critical things we want to keep track of when we're normalizing data into multiple tables is that we hold on to the cross-reference. And this is done using some entry we call a key. The key is the thing in the table that holds the primary information that can be used in another table to keep track of it. So, for example, in our little places table down right, in this slide, we have Emerita and Kaiser Augusta. In this particular table, they are unique identifiers for the row in question, and we call that the primary key. The primary key is you can think of it as the license number or passport number for that particular row in the table. And if you put it into a field in another table, which we've done in the big table in this slide, you're putting it in there for the purposes of citing that row in the other table, for keeping a relationship there. And when it's living in the coins table, as we have here, we call it the foreign key, meaning it's a key from another table that we're hanging on to so we can make that reference. Many databases will help you enforce these kinds of relationships, keep them cleaned up, and keep track of them using a series of things called integrity rules, which also derive from formalisms surrounding the normalization process. It's usually a good idea, rather than using names for things as the keys, to assign stable unique numbers to them so that mistakes are not made. And in the case of a lot of data like places, you get repeating place names, and so you don't want to use those as unique identifiers. There's a common visual formalism for thinking about these entities and their relationships between each other and how the attributes are articulated. And these are called entity relationship diagrams. And in formal database design, these entity relation diagrams are a common visualization that's used in the design and the maintenance process for a database in order to keep track of and modify and visualize all of the entities, attributes, and relationships in a database and make sure that you're programming them properly. Some software systems even provide for an interactive way to create the specifications for the database, the so-called schema, from the entity relationship diagram that's drawn visually, or vice versa. You can generate them on the fly. So here's a look at the same table we've just been examining in these different visualizations, the tabular structures between coins and places, the entity relationship diagram that showed the relationship that knits the two entity classes together. Here it is, serialized into comma-separated values, as we previously illustrated. So you've got a list of coins, and then you've got a list of places, and you'd be able to relate them by taking advantage of the relationship we described earlier. You can also put this information into a JSON construct. Here we are abbreviating the full table in order to get it on a slide that we can view, but you have a list of coins in which each little curly brace circumscribes an object of that type, and the attributes fall within it. And then you have a separate list that you call places that does the same thing for those entries again. It's also possible when thinking about data structures to foreground the relationships and to really pay attention to them, and to, instead of bundling attributes into an entity, to actually have each attribute be its own object that can be made part of a relationship. And that's what this diagram is indicating. This is one of our coins again, and it's using these arrows to describe relationships between particular things. We're giving it the number 1 as an identifying number. We're saying it is a coin. We're saying it is a quinarius, whatever that is. We're saying it was minted at something that has a number 256155, which is a place and was called emerita and was located at a particular set of coordinates. The nice thing about these kinds of structures is that you can easily add more relationships without messing with any of the other data structure. In this case, we've added the another name, another historical name to the place specification just by simply drawing another pointer and another little bubble. And you can continue to elaborate in that way. Here's an example showing adding a modern place name. We can take the arrows and dots, arrows and bubbles that we had in the previous slide and articulate them in the way I spoke them to you, but do it more formally in text. We can say this thing called 1 is a coin, it's a quinarius, it was minted at whatever. And so this kind of language, these kinds of sentences are often called triples. They are a formal structure that's used in the resource description framework, or RDF, and they serialize the kind of data construct we've been looking at, which computer scientists call a directed graph, this business of nodes with arrows that connect to other nodes. Triples are simple sentences, each with a subject, a verb, and a predicate. The particular syntax you're looking at here is called the terse RDF triple language, or turtles. There are several different such languages for working with the so-called resource description framework, and they're all designed for writing and disseminating information about directed graphs. And these are, in particular, the language of linked open data on the World Wide Web. In conclusion, I just wanted to give credit where credit was due and take blame on myself as necessary. And having done so, I think it's probably time to turn the podium back over to Dr. Bodard.
Thanks, Tom. Yeah, okay, protecting me again. So great, that's really useful, and it's particularly useful since you've talked about all but one of the data types that I'm going to mention in my part of this presentation.
I wanted to leave you something to do.
Great.
I thought that was just the charitable thing.
Yeah, thanks. So yes, so I'm also struggling slightly with presenting the slide on screen, so apologies for it not being a full screen presentation, but I'm only going to use slides for the first half of this part, and then I'm going to move on to live demonstrating on the web. So I'm going to talk about 5 types of data, most of which Tom has already talked to you about. And I'm going to very quickly mention that there are different ways of querying and of transforming, getting information out of and moving around the information from those various data types. I'm really only going to mention the first 4 in passing and show examples of them. And the examples that I will show on the slides are really there for you to go back to and look at after the session and take a little bit more time looking at and see if you can figure them out, how they do what it is I'm claiming they do, rather than attempting to teach you 5 new query languages in 20 minutes. I'm going to try and teach you 1 new query language in 20 minutes, and that's the last one. So I'm going to quickly talk about XML, which is often used for relatively flat document encoding of data. JSON, the JavaScript object notation that Tom's already mentioned, how we query database tables using the language SQL, how plain text can be queried using regular expressions, and this can also be used on the CSV, the comma separated values, and various other representations of tabular data, which can be quite useful. We've certainly had in some of the previous exercises various ways of attempting to transform and merge and move around information in CSV tables to turn them into different kinds of tables. So regular expressions will be a useful way to do that. And then finally, I'll talk about the Sparkle query language, which is designed for working with RDF of the kind that Tom's just been describing, and that's particularly useful with linked open data, which will come up in a couple of future sessions this semester. So just very, very quickly, here's a table as represented in XML. This sort of very tabular data, which is very regular, which if you look at it closely, you'll see represents the same sort of information that Tom demonstrated in database tables just now, is maybe not the most useful thing to represent in XML. Data that doesn't fit so regularly in a table can be a more useful representation. But for terms of illustration, this works fine. So here's basically a table with 3 rows. There's the primary keys 1, 2, and 3 in these rows. They have a column called type and a column called location, and you can see the content in there. I think you can probably figure out what's going on in there, even if you haven't come across XML yourself very much before. So the simplest way to query XML is to use a language called XPath, and in this particular example of XPath, we're saying in the table, go into a record and then go into the type element and give me the content of that, and potentially give me content of one of them or of all of them, as the case may be. And if you go table, record, type, that gives you the value, temple for the first one. You can also say, give me the distinct values of all types that are in the records in the table, and that would give you the values temple and agora, because temple It doesn't need to be repeated twice because it's only looking for distinct values. And this slightly more complex representation says, give me the location of any record whose type element contains the word temple, contains the string temple. So don't return to me the string temple, return to me the string, whatever string is in the location of any temple. So as I say, I'm not going to sort of labor that any further, but you might want to go back and have a look at this and see if check that you can see how this refers back to the XML example we saw a moment ago. So on to JSON. Here's another example of a representation in what is more or less JSON. For my example, I'm assuming that the JSON is being played with in Python as opposed to in JavaScript, but the principles are exactly the same, so you won't really notice the difference. And Python is particularly useful because next week we'll be learning the rudiments of Python, and you'll be able to do exactly this sort of transformation on it. So here's similarly, it's not exactly the same table, but it's a similar representation of 3 places, Dianium, Ebusus, and Iliberi, along with URIs from Wikidata and Pleiades if they exist, along with place names in Turkish and Arabic if they are available to, if they exist in this dataset. You notice that not all of the rows of the table contain the same fields because in some cases the information is missing. So we can write a simple command which simply says print in the list of places, the first place, Python counting always starts from 0. In the first place, print the value of title. Okay, and what that will print is Dianium Hemeroscopeus, as it says in the first title, the title of the first place. A second example of the sort of query we might say is for every place within this this JSON table, this JSON snippet. I shouldn't call it a table because it's not anymore. Print the title record for each one, and that will print all 3 of them, right? As you'd expect. This last snippet, slightly more complicated, I'm not going to explain how it works, says basically that attempt to print the title and the value in Turkish and the Pleiades identifier for each entry in the table. If there is any error, because one of those doesn't exist, for example, if there is no, they all have titles and Pleiades IDs, but if there is no Turkish name, then skip this one and carry on. And this will only print you Dianium and Ebusus. Those are the 2 that have values in Turkish. Anything that doesn't have a value in Turkish is skipped in this command. So these again are the sorts of things you can get out of that data. Similarly, here's another example of a table. This is a table of people, and these people each have names and locations. They have dates. Some of them have titles, and they all have bibliographical references. No prizes for guessing that this person table was taken from the IOSPE online project. And if this were in a relational database, we might want to query this using the structured query language SQL or SQL. And so we could simply have a command saying something like select ID and name from the attested persons table. And this is the attested persons table. And for each one, then it gives you the ID and the name. So it says 92 Patrikis, 93 Pavlos, etc. We might have another command which says select a distinct name from this attested persons table, which, as you can see, well, actually everybody does have a distinct name, but if there were 2 people by the same name, that name would only appear once. And we've seen this same idea earlier. And the third example here says, give me the name and the date of every person in this attested persons table whose location is Kherson. Okay, so again, the same sorts of query expressed in a different way using a relational database. And here's that exact same database table, but represented in comma-separated values in CSV, as Tom showed you. And you can see what's going on here. The only small thing to look out for is that in number 2, Patrikis, Laki Crimea is surrounded by by quotation marks because there's a comma in the value. Okay, so Laki and Crimea are not 2 separate columns in the table. They're a text value within a single column. The other thing to note is that, again, in that value between 1310 and the EOSPA string, there are 2 commas immediately after each other, representing the fact that the title field in that row of the table is empty. Okay, so there's nothing in between those two commas. So to query the CSV directly, we're going to use regular expressions, and I've given here a summary of some of the more useful commands within regular expressions. Again, I'm not going to go through this in great detail now, but this is just something for you to maybe look back at when you're going through these slides in a little bit more slowly on your own, and see what's going on. I should stress that we're going to look at regular expressions a little bit more next week, that Simona and Matteo are going to show us. So so this is something we'll come back to. Don't worry about having to understand exactly what's going on here if my little primer table here is not very clear. But what we can do with that, with these regular expressions, is we can say, find me anywhere in this table, or in each row of this table, find me a string of exactly 4 numerals, digits, in between 2 commas. Okay, so 2 commas with nothing in between them except for exactly 4 digits. And in the case of this table, that only occurs in the date field, not in every single date field, but in those date fields where the date is a single year rather than the range of years, we get exactly 4 digits between those two. Commas. And we can then, having found that information using this regular expression string, we can then use the replace string and simply say the content of those parentheses, that identified group, print it back out again. And so that would take the whole row and replace it with just the 4 digits of the date. Okay. Here's what we do when we want to find those other dates that are not just 4 digits, but are 4 digits followed by a slash, followed by 4 more digits. That represents a range of dates, a possible range of dates within which this person or this event might fall. And we might want to represent this in a different way. So we might say, show me the first set of 4 digits, which we've marked here, followed by a hyphen, followed by the second set. So we represent the range of dates with a hyphen in between, which is normally more human readable than representing it with the slash in between, as is done in the database. And for the final example, this is very complicated, but what this is basically doing is this is identifying the entire row, and so the little caret at the beginning of the line and the little dollar symbol at the end of the line mark the beginning and end of the line in the original data, and it's marking many of the contents of that row as grouped expressions, such that we can then do a replace and put those in a completely different context. So we can say, take all of that comma-separated value information, put it in an XML structure, with the values put in different places, as follows. Again, I won't go into great detail about how exactly this works or what it means. It's maybe a slightly silly example, wouldn't be the best way to do this sort of transformation anyway, but it's a way to transform data from one format to another. So my final example, before I go to do the live demo of this, is for querying RDF, or linked open data, in this form. So here's a snippet of linked open data represented using the same turtle format that Tom introduced, and this is from the numismatic linked open data repository, and this shows a range of information about a single coin HCR 23155, and the various attributes that this coin has, that it is a numismatic object, therefore a coin, that it has a title, that it has an identifier, that it is from a collection of the Ashmolean Museum, that it is from a particular type, price 153, has various numerical attributes. And then there is, below that, there is more information about this particular type, price 153, and all the various information about this, such that coins of this type are made of silver, that they were minted by Alexander III, that the mint is in Amphipolis, that it's the value of a drachma, etc. And so this is the range of information about this. Looking at this just in a little bit more detail, at just the second half of that, as Tom pointed out, you have basically a subject, a verb, and an object, or a subject, a property, and an object, as I put it here. And in the total format, the first row gives you the subject explicitly, the property, and the object explicitly. And then the semicolon at the end means that we're going to give you more properties of this same subject. So we don't need to repeat the subject after the semicolon. We only repeat the subject after the full stop, after the period, at the end of this whole snippet. And that then, presumably because we're moving to a new subject, but we could also say more about the same subject, but we'd have to give it explicitly if we were doing so. So this is as Tom said, this is the terse RDF triple language. So we could query that using this language Sparkle, which looks very similar, you'll see, to what we saw with SQL earlier, although in this case it's a slightly more complicated query, which is basically saying select, so give me the type and the weight of anything you find in this RDF query where there is a type that was created by Alexander III and that has denomination drachma, and where there is a coin of this type and where this coin has a weight. Okay, so for every, basically it's saying for every coin of the type, of a type that is a drachma of Alexander III, give me its type and its weight. Okay, and so I can show you now, if you like, I can, let me go back to the view of this in, actually I can't copy and paste from this slide. That's kind of slightly irritating, so hang on. I need to go, pretend I'm copy and pasting from that slide. I'm going to go invisibly to you to another window where I can copy and paste it from, and paste it into the SQL search box, the Sparkle search box, and so show you that actually happening. Am I now showing you the Sparkle search box? Yeah. Okay, so I'm now looking at the Nomisma website, and the Nomisma website very helpfully has a list of examples of Sparkle queries that you can use, which we'll come back to in a moment. And they also have this Sparkle endpoint, which has a query in this box. So I will delete what they've put in the example query they've given us in this box, and I will paste in that query that I just got from the slide, and I'll hope that I haven't made any mistakes in it. And just to so quickly go through this again, what this is doing is this is first declaring the prefixes, because all of the entities in this RDF are represented by full URIs, full URLs, and in fact, in practice, almost all of these URIs you could paste into a browser, and you would get some information back about them. So where we see something here that says NMO has authority, that obviously you couldn't paste that into a browser and get anything back. But if you replace NMO with this initial part of a URL and then add has authority to the end of that after the hash sign, then you would get information back about what has authority means in the Nomisma ontology. So, and so then it gives you the information. There's two ontologies represented, NM and MNMO, both of which are Nomisma defined, and so yes, it's saying give me the type and the weight of any coin that has a weight in a type that has Alexander III as an authority and that is of type drachma, is of denomination drachma. Okay, so that's the syntax is a little bit circuitous from the point of view of someone trying to express that in English, but that's what it's asking us for. And if I simply submit that query, it will return to me a list of coin types, well, coin instances, and for each coin instance, it will return the type, which in this case, price 153, as the one we've just seen, but there are a few others as well, price 1501, price 1502, price 1505, and the weight of each coin within that type. Okay, so we've got a result of that in that table. And I, in fact, took that query almost verbatim from one of the ones in here. So I forget which one it was I took it from, but yes, I took the all weights of Augustan denarii, and instead I changed it to represent all weights of Alexander's drachmae. But that gives us the same, basically the same kind of query. So so what I want to do now, and I'm not going to spend very much time doing this here on screen, but what I want to basically show, and what I want to ask you as students to do in the exercise for this session, is to take one of these queries. You can take any one of these queries, where we simply copy the entire RDF, making sure the entire Sparkle example, and making sure not to miss the prefixes, and making sure not to miss this closing curly brace at the end. Go back to the Sparkle query window, paste that in, and do the search. So you see here, this is a list of all the Roman emperors indeed, and then see if we can tweak this information to get a different kind of information out of it. And I chose a poor example because I would have to tweak something. I would have to say, I don't know what. I would maybe have to change a different kind of role, but I don't know what other kinds of roles the Numisma database has. Does anyone else happen to know off the top of their head what other roles you will find in Numisma? If not, I'll choose a different example. No, let's find a different example then. So this one's easy. Find all hordes found within 50 kilometers of Goranu, Romania. And this, so we copy this in here. There's several things we could change in here if we wanted to put in a slightly different query. So here I'll just do the query as written, and you'll see there are maybe about 10 such hordes, 8 such hordes. I mean, these are all the hordes that were found within 50 kilometers of Goranu. The horde of Goranu, of course, is found among them. That's within 0 kilometers. But so you can see a little bit how the query is expressed. So it's saying, find me all the information. So find me anything where there is a location that is within 50 kilometers of this point on the map represented by standard coordinates. And tell me, yes, find me anything that is that close, and so for any location that is that close to that point, find me any horde whose find spot is at that location, and that is a horde. I mean, horde is just a variable here. That could be anything. That could be an X. So find me any entity X that has a find spot at that location, and that is a horde, and that has a label, that has a title. And if it has a closing date, give us that as well. And look for the label, I guess, in English specifically. And so, again, what it does, it gives us the location, which is a place. In this case, it's a geonames identifier. Give me the horde that is represented at that location. Give me the label that's associated with that horde, and there's the date associated with that horde given as well. That's the closing date of that horde, if there is one, which in this case all of them do. All of them do seem to have a closing date. So we can change all sorts of things in here, right? We can look for hordes within 100 kilometers instead. We could, and that gives us a larger number. we could look for hordes within only 25 kilometers, and that would give us a smaller number, presumably. We could, if we wanted to just make stuff up, we could look for a completely different set of coordinates. I don't know what's at that set of coordinates, but let's just put in some random coordinates and see what happens. Nothing. Presumably I found a point in the middle of the sea or something. Let's try 42, but 5, and let's have a slightly wider range. So, okay, I found a point that's presumably somewhere in between Spain and France, as we found 2 hordes found in Spain and 1 found in France, as a result of that search. And you know, if you were doing this exercise, you'd take a little bit more time and go and look up the actual coordinates of a place you're interested in, rather than that. So, as I say, for the exercise, what I'd suggest is going to this list of Sparkle examples, tweaking easy things of the kind I've done, and also try to work out what you would do if you wanted to completely change the query to ask something slightly different. So not just changing the values and changing the names, but try to change something slightly more different, just to get the sense that you're understanding what's going on with this Sparkle query. And it may be that 2 times out of 3 you'll attempt a Sparkle query that will give you no results, or it will just say this is broken, this is not valid Sparkle. But that'll be a part of the learning curve. So I think that's fine. Okay, so I've gone on for too long already. I'll hand you over to Rada, who is going to talk about visualization for a few minutes.
Thank you, Gabby. I will go directly to the presentation. So the last part of today's session is on data visualization. Please let me know if you can see my screen sharing well, and if you can hear me, of course.
Yep, looks okay.
Good. So we generally think of data visualizations as relatively modern elements, but actually they go back a long time. So in the first part of the presentation, I will just say a couple of words on the history of data visualizing. Afterwards, we will go into the analytical part and see what we visualize today and why do we do it. And finally, I will show you some examples and some exercises. The first data visualizations had a very practical purpose, of course. So this is Tabula Peutingeriana, theoretically based on a 1st century AD itinerary, and it shows roads of the Roman Empire, roads connecting the cities. So they made a drawing, a visualization with a very clear purpose. This is Rome. This is just a fragment of the itinerary because it goes from Britannia to the Indias, to the end of the world, so to speak. Afterwards, visualizations were made. Of course, I am simplifying matters a lot, but afterwards, people needed to visualize things which were sort of abstract, and they were difficult to understand for the general public. This is a drawing, basically explaining how the eclipses take place and why we see an eclipse. As you can see, it's from the beginning of the 18th century. Only much later, visualizations were connected to more abstract data. And during the 19th century, we basically have the first statistical visualizations, the first pie charts and circle graphs. The Playfair graphs are quite famous as they are very complex for the time being, and we have to realize that every calculation and every graph was made by hand, of course. This one, the one you can see on the screen, represents the levels of taxation in different European states at the beginning of the 19th century. The 19th century was the golden age of statistics, so to speak. Everybody was interested in it, and a lot of visualizations of this kind were developed and were printed in newspapers and books and everywhere. At the beginning of the 20th century, visualizations sort of went out of trend. One of the causes being that without a very quick technical development in computer sciences and IT, what we call today, of course, computer sciences and IT, you wouldn't call them that at the beginning of the century. Without these advances, you couldn't say much more than you could have said during the 19th century. The interest for data visualizing re-emerged powerfully during the 70s. And we still live in that trend today. What do we have today? In what has been developed during the last 35, 40 years in data visualization? So we have now highly interactive systems. We have applications of visual models in a wide range of domains and with various purposes. And we, as historians and classicists, are situated here, actually. Because this was not these are not the first fields in which people applied data visualizing. As well, new methods for visualizing complex data and statistical and graphical software have been developed. And data manipulation possibilities were as well. Of the visualizations increased and required more clean data, let's say. But nonetheless, why do we visualize data? For communication purposes, because we want to focus on certain aspects and we want to make these aspects easier to understand for our audiences. And for research purposes, we want and try to identify patterns otherwise invisible. And why not visualize data? As this might already imply, because focusing on certain points sometimes distracts from other points, potentially equally important. This can be unintentional or intentional. As well, it implies a generalization and thus it simplifies reality. That's why some people say that discourages complex thinking. And it can discourage direct interaction, especially in classes during the teaching act. I don't say that PowerPoint is evil, as was the title of an article I've read a couple of days ago. I just say that we have to be aware to rationalize how and why we use all kinds of visualizations. What do I visualize today in humanities and in classics? Generally, these types of information, not exclusively, but as we've already decided upon, we use visualization to focus on certain aspects on which we want to focus. What kind of data do we need to employ in visualizations for ancient history and for classics in order to get results? Lately, everybody is trying to work with big data or would like to work with big data. How do we define big data? So canonically, it means data beyond the ability of commonly used software to capture, curate, and manage. In demography or sociology, this means millions of entries. Generally, for historians, a couple of tens of thousands of data is considered in quality big data. But in order to get really relevant visualizations and in order to use them for research purposes, so for identifying patterns otherwise invisible, we have to use rather smart data rather than big data. The idea is to select our data and to structure it in such a way that we can get to relevant results. Now, presenting some resources and some exercises. Let me come back on here. Okay, so this platform, Seeing Data, is quite good for, especially for learning. It has a lot of general stuff on visualizations, and as well it has a couple of projects which work with very different data sets and with very different visualization types. Here you also have the link, of course, to the original project. As you can see, the visuals look very different, and the data sets used are very different in essence as well. That's why it's useful when you try to learn about data visualization and try to make sense about how you can actually use this for your own research. It might be useful to take a look here. This Tableau Public is a platform which allows us to create visual representations of data. But last year we also had in Sunoikisis a session on data visualization, and in that session they have used Tableau Public for the examples and exercises. So if you want to see how it works, you should go to the recording of that particular session. For this session, I'm going to use row graphs in order to exemplify some visualizations. Before that, I want to mention that there are many more platforms which are very good for visualizing data. Row graphs are quite easy to use, as you will see on one side. On the other side, there are a lot of platforms which imply geographical visualizations. You have already seen that, and they have been explained by persons far more competent in this than I am during the last sessions of Sunoikisis, which are quite connected to geographical representations and visualizations. As well, there are other platforms as Table2Net, for example, which focus on visualizing networks. A couple of weeks from now, we will have a session on network analysis. So I will not go to that part of the visualization either. Good. This is row graphs. As I said, is a platform quite easy to use. We just go here. And for the beginning, let's try and look at their examples. These are a couple of data sets they provide. What's very interesting, and you should look at this, is that here they actually say the kind of visualization, which is best fitted for each data set. If you do not use a provided sample like these ones, you have to pay attention to how you visualize your own data. So let's go to this music industry, which is a time series, they tell us. So let's choose. You have here a multitude of visual possibilities, and let's choose an area graph. These fields are the required fields, and here they tell us what kind of columns can be employed. So numbers, strings, dates, and only numbers. We can use here the market share. For the date, we will use the year, and for the size, we will use the media. But we cannot do this because this is a string. So here, and the market share here. And we get this. We have the years, we have the media, and we have the market share. As you can see, we have a lot of stuff. So we have here the vinyl singles, which obviously decreased dramatically after 1990, for example. You can enlarge the visualization if you need to, and here we can download it as a vector graphics, as a simple image, or the JSON, so the data model if we want to reuse it or whatever. Now let's see from an URL. I will use this. I won't go all the way with the visualization so that you can do it. We have to go to the raw data, otherwise, of course, the URL will not work because the previous one was for the whole GitHub page. We'll put it here. And we'll look what kind of information we have here. We have two numbers and a string. So we have to make some kind of visualization which would make sense in this idea. We could actually try this dispersation plot, which was suggested automatically. And we can put the numbers on the axis. We don't have a size. I don't know if we should use a color. And the label is the title of each book. Well, we have a lot of labels, and this is a graph which definitely should be increased, enlarged a lot in order that we can see something on it. Unlike more sophisticated visualization tools, we cannot determine the size of the font ourselves. And as you can see, if we have, as we have here, columns with no heading, because here we don't have a header line, a heading of the columns, we will just see here the first column. It's quite logical, but let's try a different visualization for this. So a cluster. Let's say like this. Well, as you can see, this is dramatic. We cannot understand anything. So if we want to make a cluster, we should... my touchpad is not working so well. That's why you're seeing this. Okay. Apparently it doesn't like this particular visualization. So what I meant to say was that we should remove the labels and simply not use them anymore and visualize the cluster, but you can do that as part of the exercise afterwards. And the final possibility is to upload our own file. Okay. Excuse me for this. Maybe I should just reopen the website. Okay, and we can upload our own file. I have here a file prepared. It has the Roman governor's guard in it. So let's make a cluster. Let's the attribute, which is a number, is a dating. As these are my own data, I know what the attribute means. And we can color them by province, let's say, and it looks like this. It doesn't say that much. And if we want a label, we can of course put the names on them, as I already had a label field, which is the name of each person. Let me show you how we can increase it a bit if we want to. And as well, we can increase this, so to better see it. But it's okay-ish, but you don't get so much of the idea, isn't it? So maybe a different type of visualization would be better. Let's try this. Here, the nice part is that you put something, the label, and I have all of their names. That's cool. Now I can actually read them. But let's see how they were distributed by province. And I put in province above label. And I have this distribution, which is nice. I know each person from which province exactly came. But I also want a temporal idea on this. So I can put this here. No, here. Okay, we can put it wherever we want it. We can put it here. And so we have the provinces as the time distribution. Each number represents half a century. Or we can do it the other way around. And we have the time period and provinces and main attestations. So the idea is that this is a very easy to use resource if you know your data and you know what you want to obtain from that data. And the exercises suggested here go exactly for this. Okay, I think this is it. Thank you.
Thanks a lot, Rada. That's great.
Thank you very much.
So yes, and one thing we might do. So both of those examples, both of those exercises that we've given are very much free. So the students can come to the exercises. They look at the tools or the websites that we provided in both cases, and play around with the data, play around with some of the data we've given, some of the data they brought themselves, some of the data that comes with the site itself. For the terms of the visualization, in terms of the Sparkle exercise, it's entirely working with the data that's on the site, and we're not going to bring our own RDF in and try and query that. So it's more or less free. Try it out, challenge yourself, try and do things and see if you've understood what these technologies are for by coming up with ideas for what you want to do with them, and then see if you can figure out how to do them. And so the idea is then to come to class if you're having taken this as part of class in the following week, bringing your examples and be prepared to say what you were trying to do with these examples, what worked and what didn't, show the things that did, ask for help with the things that didn't, and try that. And that in both exercises, I think that would be that'd be a useful thing to do. What we might do is perhaps we might quickly brainstorm after this session a couple more sources of data that we might add to that list. So people who haven't got their own complex multi-column data to play with, we could give them some more data or point them to some more data to put in there. But people may be able to find their own as well. But maybe we'll try and find a couple more things in there and see what we can add to that list. But no, so that's great. I think that's. Does anyone else have any questions or anything they want to add about any of the things we've talked about so far this afternoon, or evening or morning, depending on where in the world we are? I'm looking at the YouTube page, and no one has left any questions on there immediately.
Well, this means we are right on time.
Yeah, basically. Yeah. Good. Yeah, and so I think I'd just highlight the the connections between this and other sessions. We've deliberately avoided talking about geographic data in this session because we've just come out of a series of 3 sessions on geographic data. But a lot of the principles we've talked about here, I think, will be easily applicable to that data and will in fact fill some gaps. You've been looking in the last couple of weeks at some data that's been given to you in JSON format or in CSV format, and you might have just sort of taken that at its face value and just taken the JSON, put it in the site, and then hoped it would go away. But now maybe you understand a little bit more about what JSON is, and that's probably useful. And if you have a site that requires JSON as input and you've only got CSV, you now know a little bit more maybe what it might involve taking that CSV and turning it into JSON. I wouldn't like to have to try and do that by hand, but luckily next week, to move in the other direction, you'll see, you'll learn some skills which will precisely enable you to take something in a clear tabular format and turn it into another clear tabular format, such as moving from CSV to JSON to XML and various other formats like that. And those sort of things will be presumably potentially be useful both for the things we've done in the past in terms of transforming geographic data, in terms of transforming and visualizing data of the kind we're talking about this week, and of the sort of things we're going to talk about in future weeks of other kinds of data that we'll come across, including 3D data and so forth. So there will be various things that that will be useful coming out of this, I think. And so I think we can. Maybe there'll be more discussion. I mean, maybe this has been a very sort of informative session, which may not be quite so conceptual and theoretical that needs a lot of discussion in the way that that some other sessions do. So yeah, unless anyone has anything else they want to add right now, I think we might leave it here. Great. So thanks very much, everyone. See you all next week.